So hello guys, welcome to our channel Niperian Solutions. So today we are going to discuss about the infrared spectroscopy. So previously we have covered with the nuclear magnetic resonance, that is the NMR spectroscopy. So today we are going to discuss about the IR spectroscopy. Okay, so let's see one by one, right? So here the first question is, which of the following shows near infrared region, right? So what are the options here? 2.5 micron to 15 micron, 0.8 micron to 2.5 micron, 15 micron to 200 micron, and the none of the above, right? So what is the right answer here? Here the right answer is 0.8 to 2.5 micron. So these values are given in the micron, but you have to know the ranges in the that centimeter inverse also, right? Okay, so here are the ranges of the near IR, that mid IR or far IR. Okay, so in the wavelength they are giving in the micron ranges, and wave number they are giving in the centimeter inverse. So here you can see the range of 0.8 to 2.5 micron, that is also 12,500 to 4,000 centimeters. One and the same things, just unit is changing. One is given in the wavelength, that is in the micron, and the wave number, that is in the centimeter inverse. In the IR, that is the 2.5 micron to 15 micron, and the wave number is 4,000 to 667 centimeter inverse. And similarly in the far IR also, right? So these are the ranges. So please remember this one. Okay, so the next question. Among the following IR vibration of carbon dioxide, which is IR inactive, right? So the options are symmetric stretching, asymmetric stretching, bending, and rocking. Okay, so these are the stretching and bending, right? So these are the vibrations of the IR, but which one of the following is the IR inactive, right? So carbon dioxide having the different stretching and bendings. So which one is the IR inactive? Right, so what is the answer here? That is the symmetric stretching, right? So it is IR inactive. Let's see how it is IR inactive. So here we can see the principle of IR, that is the net change in the dipole moment. So that is very basic principle of the IR, very important. If there is a dipole moment in the molecule, then and then only it is IR active. If there is a net dipole moment is 0, then these are IR inactive molecules. So just see, if a molecule has a center of symmetry, then the vibrations are centrosymmetric and IR inactive, right? But are active in the Raman spectroscopy, right? And the vibrations which are not centrosymmetric are active in IR but inactive in Raman spectroscopy, right? So similarly here we are looking the example of carbon dioxide, right? So in the first one, that is the symmetric stretching. So here the net dipole moment is 0. So that's why that is IR inactive. That is our answer, right? So that's why the symmetric stretching of the carbon dioxide, that is the IR inactive. In second one, there is also stretching, but that is the asymmetric one. So the vibrational frequency at the 2350 centimeter inverse, and the bending shows 667 centimeter inverse. So these are the values of the carbon dioxide. I hope this is clear to you. Okay, so there are the different vibrations in IR spectroscopy. So there are mainly two types. First one is the stretching and another one is a bending, right? So in stretching, again there are two types, symmetric and asymmetric. So what is the symmetric? The movement of the atom in the same directions. Like, so in diagram here you can see the symmetric, right? And in asymmetric, one atom approaches the central atom while the other departs from it, right? In this one, right? So in bending vibrations, also called as the deformations. So again two types, in plane vibrations and out of plane vibrations. So in plane vibrations, scissoring and rocking are the example of in plane, and wagging and the twisting are the examples of out of plane vibrations. Okay. So next, the value of stretching vibrational frequency of a bond can be calculated. Beer's law, Fick's law, Hooke's law, and Pascal's triangle, right? So what is the answer here? Here is the right Hooke's law, because based on the Hooke's law we are calculating the vibrational frequency, right? So what is the Beer-Lambert's law? So that is nothing but in UV spectroscopy we are calculating the like absorption is directly proportional to the concentration. That is nothing but the Beer's law. Then Fick's law is related to the diffusion, right? Then Pascal's triangle, where we have seen the Pascal's triangle, that is in the NMR for the multiplicity like singlet, doublet, triplet. So in Pascal triangle we are seen that all the multiplicities. So the next question, okay, so before going to the next question, just see the what is the Hooke's law, right? So the wave number is equal to 1 divided by 2 pi c in root k upon mu. And what is that mu? Mu is nothing but the reduced mass. So here the formula also given, right? So the according to the formula there is a very strict like what we can say, the value of vibrational frequency depends upon. So right, so what are the like on what factors that depends upon? That is the k and mu. So what is the k? K is nothing but the force constant, or what we can say, that is the bond strength. And second one is the mu. Mu is nothing but the reduced mass. So depending on these two factors our wave number we are calculating, right? So if bond strength increases, vibrational frequency increases, right? As the bond strength increases, vibrational frequency increases. And if reduced mass decreases, the value of vibrational frequency increases. Means simply we can say the wave number is directly proportional to the bond strength and inversely proportional to the reduced mass. So here we can see the example, right? C triple bond C, C double bond C, and C single bond C. So as the bond strength, right, so bond strength here decreases, right? What we can say, the triple bond, then double bond, and then the single bond. So bond strength decreases, so vibrational frequency also decreases. So what we can say, that is the directly proportional to the bond strength, right? In second example, what is here, right? In second one, so if we are saying that the reduced mass, that is the example of reduced mass. So what is here? So all the atoms attached to the carbon. In first hydrogen is there, then carbon, oxygen, chlorine, bromine, and iodine. So among these all the molecules, the hydrogen has lowest mass and the iodine has the highest mass, right? So means whatever the like atom which is having the lowest reduced mass, which is having the highest frequency, that is the CH, right? CH, the lowest reduced mass, and here this Ci, right? It is having the highest mass, highest reduced mass, right? So by taking these two examples, if the reduced mass is lowest, then the vibrational frequency is highest. Means simply the vibrational frequency is inversely proportional to that of the reduced mass. Okay. So the next one, for a linear molecule such as HCl, the number of modes of vibration are, right? So again that is very important one, right? So the options are 0, 1, 2 and 3, right? So before going to the number of modes of vibration, we have to know, so what are the number of modes of vibration, right? Okay. Here the vibrational degree of freedom for linear molecule, that is the formula is 3n minus 5, and for non-linear molecule, that is the 3n minus 6. So the degree of freedom, the formula is translational vibrations plus rotational vibrations plus vibrational vibrations, right? So here that formula is here, right? So if we are calculating like the vibrational frequency, right? We know the vibrational frequency. So the formula is like vibrational frequency or the vibrational degree of freedom is equal to 3n minus translational minus rotational. So just move the translational and rotational to the left side. So the formula is like vibrational is equal to 3n minus translational minus rotational, right? So here are the formulas 3n minus 5 for the linear molecule and the 3n minus 6, right? Here are 3n minus 5 and the 3n minus 6. So for linear molecule and non-linear molecules. Okay, I hope that is clear, right? Okay, now we are moving to the question here. So for a linear molecule such as HCl, the number of modes of vibration are, right? So in HCl, how many atoms are there? That hydrogen, right, and the chlorine, right? Means total 2 atoms are there. Okay, so here n is equal to 2, right? What is the value of n here? That is the 2, right? So 3n minus 5, right? What is our formula? 3n minus 5. But for what? For the linear compounds. So n is 2, then 3 into 2, that is the 6 minus 5 is equal to 1, right? So what is the answer here? So our answer is 1. Okay. So for similarly for non-linear molecules, the formula is 3n minus 6, right? And depending on the molecule, we are calculating the modes of vibration, right? So here are for linear molecules as well as for non-linear molecules. Here the total degree of freedom is always 3n, right? This one, total degree of freedom is always 3n, and the translational degree of freedom is also always 3, right? That second one. But here the just change is in the linear molecules, the rotational degree of freedom is 2, and for the non-linear molecules, the rotational degree of freedom is 3, right? Because in a non-linear molecule there are 3 different axes, right? So just you have to remember the formula for linear molecule as well as non-linear molecules. Okay. So the next one, the factor on which the wave number of absorption depends in infrared spectroscopy is inductive effect, mesomeric effect, field effect, and all of the above. So right, what is the answer here? That is the all of the above, because higher frequency is depending on the inductive effect, that is the plus I and minus I, then mesomeric effect, then field effect also. So these all the effects are very important in the IR spectroscopy. So next, in infrared spectroscopy, the pair of isomers which cannot be distinguished is R, right? So that question is very important. So cis trans isomers, functional isomers, enantiomers, and positional isomers, right? So what is the answer here? Our answer is the enantiomers, because in IR spectroscopy, cis trans isomerisms, functional isomerisms, and position isomers we can distinguish, right? Because these are having the different wave numbers or the different vibrational frequencies, but we cannot distinguish, right? We cannot distinguish the enantiomers in the IR spectroscopy. Next, the region below 1500 centimeter inverse is called a functional group region, fingerprint region, overtone region, and all of the above, right? So what is the answer? Whatever the values which is below the 1500 centimeter inverse, that is the fingerprint region. Okay, so what is the functional group region? That is nothing but the 4000 to 1500 centimeter inverse, that is the functional group region, right? Okay, so here are the values of the functional group region and the fingerprint region. So 4000 here, from 4000 to up to here, right? Like 4000 to 1500, that is the functional group region, and for 1500 to 600, that is nothing but the fingerprint region. So why this is the functional group region? Because mostly all the compounds that we are studying in IR spectroscopy, these values are in the this area only, 4000 to 1500. So all the functional groups are in between the this region. So that's why this is the functional group region, right? And here you can see what is the graph of that IR spectra, that is the wave number in centimeter inverse versus transmittance, right? Transmittance in the percent transmittance, right? So that is also very important question, right? Wave number versus the transmittance, percent transmittance. Okay, the next question, which of the following cannot used as solvent in IR, right? chloroform, water, carbon tetrachloride and carbon disulfide. So what is the answer here? Our answer is water. We are not using water as a solvent in the IR spectroscopy, right? Similarly, previously we have seen the solvents in NMR, right? So deuterated solvents we are using in the NMRs like CdCl3, then carbon tetrachloride also we are using. So these are the solvents in the NMR. So here water we are not using in the IR. The effect of hybridization on vibrational frequency is, right? So there are the different hybridizations of the molecules. So depending on that, so which hybridization strategy that we are using in the IR spectroscopy, right? So what is the vibrational frequency? So effect of hybridization on vibrational frequency. So what is the options are here? Sp is greater than sp2 is greater than sp3, sp2 is greater than sp3 is greater than sp, sp2 is greater than sp is greater than sp3, and the last one sp is greater than sp3 is greater than sp2, right? So what is the correct answer here? In IR, what is the hybridization? So that is nothing but the option A. Sp is always greater than sp2 and which is greater than sp3, right? Okay, we will see how it works, right? So in here, in the first compound, that is the sp hybridized, second one is the sp2 hybridized, and third one is the sp3 hybridized. So in sp hybridized, the wave number, that is the 3300 centimeter inverse. In sp2 hybridized, that is the 3100 centimeter inverse, and in sp3 hybridized, that is the 2900 centimeter inverse. So clear? So in NMR we have seen the hybridization, that is the sp2 hybridized, then sp hybridized, and then sp3 hybridized. So please remember these two like hybridization effect on the IR and NMR also, right? So in IR, right? So here, as the p character increases, right? As p character increases, the wave number decreases, right? So please remember this one also. Okay. So the next one, the vibrational frequency in IR has a graph. So just recently we have seen. So what is the answer here? So no need to explain again. So percent transmitter versus wave number in centimeter inverse, right? Okay. So here are some like important points from the IR. So the sampling techniques, right? So how to prepare the sample and all the things in IR spectroscopy. So generally potassium bromide or the sodium chloride we are using for the preparation of the sample, right? So KBR is showing the value of 4000 to 400 centimeter inverse, and the sodium chloride, that is showing the value of 4000 to 650 centimeter inverse. So again some solid materials, so we are that are the mulling techniques. So in that mulling techniques we are making a paste of that any like paste type of compound, and that we are using for the preparation of the sample. So generally in solid form, the nuzole, that is the mineral oil that we are using, hexachlorobutadiene, and the chlorofluorocarbon oil. So these are the compounds we are using in the solid. So the disadvantage, so mostly we are using nuzole, commonly used, right, that mineral oil, but the disadvantages is that so nuzole itself showing so the different IR spectra at 2924 centimeter inverse, 1462 centimeter inverse, and 1377 centimeter inverse. So this is very important, right? So you have to remember these values, because in most of the time they are asking what are the absorption values of the nuzole oil itself, right? So that is the disadvantage actually, but they are asking the what are the IR frequencies of nuzole oil. Then again carbon tetrachloride we are using, just previously we have seen the solvents used, that is the carbon tetrachloride. So that is the strong stretching, that is 785 centimeter inverse showing for the CCl stretch, right? And the NH stretch is showing the sharp band, and the OH stretch, that is showing the broad band in the IR spectroscopy. Okay, here is very important, the ring size effect with internal double bond, right? In IR spectroscopy, what is the effect of that ring size in an internal double bond, right? So here we can see in the first one that like 7 membered ring, then 6 membered ring, right, then 5 membered, 4 membered, and here is a cyclopropane ring, right. So as our ring size decreases from here to here, as ring size decreases, right, so our value is also decreasing, right, like 1650 centimeter inverse, then 1646 here, right, then 1611, 1566. But again here in cyclopropane the 1656, right, so means this effect is only from up to butane ring, right. So in the cyclopropane ring it is showing the higher vibrational frequency, right. So that is very important. Okay, the next one, the effect of alkyl substitution. So that is also very directly proportional to the vibrational frequency, right. So as if you are adding one alkyl group here, right, here is just a cyclopropyl ring. So if you are adding the one alkyl substitution, so that value increases from 1656 to the 1788, and again it is increasing if you are adding the one more alkyl substitution, so that is the 1883, right. So similarly in this one also, in butane ring also, so as the alkyl substitution increases, right, so the vibrational frequency also increases. Okay, the next one, the effect of exocyclic double bond. So similarly here what is happening, so in alene that the value is 1940 centimeter inverse, in second one that cyclopropene and that exocyclic double bond means cyclopropane, butane, pentane, hexane, right. So this is also the decreasing as the ring size increases. What is the effect here? As the ring size increases, then the value of that vibrational frequency are decreases, means that is the inversely proportional to the ring size in exocyclic double bonds, right. And here is the last one, that is the very important, because generally they are asking in exams for the different vibrational frequency of the carbonyl groups. There are many functional groups in the carbonyl groups. So first one is the anhydrides, that is the 1810 centimeter inverse, then acid chloride, anhydrides, that is band 1 and band 2 of the anhydrides, right, then ester, aldehyde, ketone, carboxylic acid and amide. So these are the characteristics IR vibrational frequencies of the carbonyl compound. So you have to remember each and every carbonyl compound with their vibrational frequencies, right. Okay, so thank you guys. So for today we have completed the IR spectroscopy. Definitely in the next video we will see the another spectroscopy technique with all the MCQs and the explanation. So please subscribe the channel and share with your friends. All the best. Thank you.